HashMap, which is one of the fastest data structure, is built using an array. But although it uses the array, it is much faster than the array itself, which takes big of n time to search for an element. So what is making it much more efficient than the array, which it is highly dependent on? Let's find out. So the array inside holds something special, not just the data we wanted to store. It holds an object called node, which contains a key and value which we wanted to save, a hash, which HashMap uses for locating the data, and next, which points to an address location in case of mapping issues. We'll talk about this in detail as we proceed. So when we are trying to save the data, we need an index to save it. This index is calculated by the HashMap based upon the key which we pass. So next time when we want to get the data, HashMap can get it just using the key. This index calculation is done with the help of hashcode method. This is an inbuilt method for every object, and this helps in giving a unique large number based upon the input given. And that number is not random and will be the same each time when the same input is given. So we have a way to convert a key into some number, but this number is large and we need a way to convert this into an index. So for this, as we need the index less than the array length, HashMap makes use of Bitwise AND to get the index. The array length is always in powers of 2, so the length of the array minus 1 bit value always consists of all ones. So the AND operation between the array length minus 1 and the hash gives us only the bits less than the array length, and hence we get a valid index. This way we get the index from the key with the help of hashcode and some basic math. But there is an issue with this hashcode method. When the strings are similar, the lower bits won't change much. Since the AND operation is filtering the bits less than the array length, those are mostly of lower order, and hence strings might produce the same hash value, which means both end up at the same index. We call this a collision. Because of this problem, HashMap doesn't perform the index calculation on raw hash. It first spreads the bits with these mathematical operations. This operation shifts the bits to the right, and we make use of XOR for mixing the bits with the original hash code. This creates much unique hash value than before, and the collisions are reduced drastically. There is still some possibility that two keys might end up with the same hash value even after these calculations. So if the collision happens, HashMap forms a linked list between these two, as these are linked by the same hash value. And while traversing the data, it just manually traverses each node in that linked list and checks the key if it is matching using the equals method to find the correct match for retrieving the data. But the linked list is no way better when it comes to traversing for searching an element. We need to traverse the complete list until we find the right key. This decreases the performance if the list size increases. So when the linked list becomes crowded, it is converted into red-black tree automatically. This is much faster than the linked list. HashMap also resizes automatically when the total entries exceed a threshold. This is called a load factor. When the number of stored entries crosses the capacity, the HashMap array automatically increases its size. It doubles the array and rearranges all the existing keys into their new positions in the bigger array. Because of all these operations, HashMap becomes extremely fast than a normal array for fetching the data, as it can fetch the data directly with the help of key and some math instead of complete traversal. Thank you for watching. Please consider hitting the like button and subscribe to the channel if you found this helpful. See you again in the next one.